So in the last few videos, we've seen waves kind of like this, oscillating back and forth, and we just kind of assumed that they obeyed these sine and cosine relationships, that was what governed them. We didn't actually, put in the physics of what's going on inside the wave, between the atoms of the wave. So in this last video about waves, that's what we're going to look at, is how do the atoms in a wave interact with each other? How does this wave motion actually end up taking place? So we've got here as a wave constructed now of atoms. Instead of just being points that obey a nice clean cosine function, we've got a list of atoms. Here is where we create our atoms. Again, we're just storing them in a list. Each atom gets a sphere shape. And then down here is where you create the initial shape for the wave. So we're starting out in this scenario with a sine function, a nice clean sine function. It does not stay quite that clean for very long, as you can tell. And so in our animation loop, what we're looking for is the force that each atom experiences. Each atom experiences a force based on its two neighbors. So if I'm atom number n, then I'm looking for the atom to my left, that's atom n minus 1, and I'm looking at the atom to my right, atom n plus 1, right? So if I'm this atom, I'm concerned about my separation from this atom and this atom. I don't really care about the atoms over here because I'm not connected to them directly, right? They're all connected through each other, but I only have two nearest neighbors. And so what we do, we just loop over this. We use the same spring force that you've seen before. That's equal to negative spring stiffness times the distance between the two compared to equilibrium, and then moving them in a direction toward equilibrium. So if they're too close to each other, they will be pushed apart. If they are too far away, they will be pulled together. We want the atoms to move toward equilibrium. And so you can see we get very similar behavior to what we had before. It's a lot coarser than what we had before because these atoms are pretty far apart. You can change that by making the atoms closer together. So let's suppose I go from a dx of 0.2 to a dx of 0.1. Here my atoms are closer together. It's a much smoother curve, and I get much smoother behavior out of this. It's still kind of interesting to get that little jagged edge right there. Again, because this is behaving physically. It's not, it's not idealized like we had in the last few videos. But when you think about this, the atoms in a string or in a sound wave or something are much closer together than this, and so that's why you do get smooth waves in real life, is because the atoms are really, really, really close together. But the fun part for this is you can set this initial shape to be anything you want. So let's comment this out for a second. Let's suppose we made this atom.pos.y equals absolute value of atom.position.x. Absolute value function looks like this, of course. And oh yeah, these 2 points stay fixed together. So we might want to move this down by 1, 2, 3. Let's move that down by 3 just so it stays in the grid there. There we go. So now we've pulled it down like this. It's kind of like plucking a guitar string a little bit. It's more like releasing a guitar string. And so you can play around with whatever kind of shape at the beginning that you want and see how it evolves. You can see, does it ever return to that original shape? Do we end up with something that ends up undulating back and forth? Oh, so there we got a mirror of our original absolute value function. Let's see if it returns back to the original. You could try a sine wave with a different wavelength. You could try adding together a couple different sine waves. There are lots of different things you can play around with this. And sure enough, here we get back to our original absolute value shape. You notice the atoms are shaking a little bit along here, so that's causing some distortions in the shape. But anyway, and the activities at the end of this video, you'll play around with this shape, see what you can learn about waves from there, and just evaluate, do you think our idealized picture of a wave really matches up? So thanks so much for watching. I will see you next time. Bye-bye.